Welcome to Jeremy's IT Lab. This is a complete course for the CCNP ENCOR Enterprise Core exam. In this lab, we will generate and examine the ICMP message types we looked at in the lecture video by using debugs and packet captures. First, let's check out the network topology. There are three segments. First is the one here with R1, R2, R3, and PC1. It's 192.168.123.0/24. Then the link between R2 and R4 is 192.168.24.0/24. And R4's LAN is 192.168.4.0/24. Each router's IP addresses end with the router number. .1 for R1, .2 for R2, .3 for R3, and .4 for R4. PC1 and Server 1's IP addresses are .10. Let's look at the lab instructions. What we're going to do is start a couple packet captures and also initiate a debug on R3 to display log messages when it receives ICMP messages. Then we'll send some messages from PC1 and R3 to Server 1 to generate ICMP messages of each of the types we looked at in the lecture video: redirect, destination unreachable, time exceeded, echo request, and echo reply. Echo request and reply are easy, of course. We can generate them by simply sending pings, so we'll focus on the others. First, I'll initiate the packet captures. PC1's default gateway is R1, and R3 has a default route to R1 as well. If we try to ping Server 1 from either device, R1 will send a redirect message to them, saying that they should send the packets to R2 instead. I want to capture those redirect messages, so I'll do a packet capture on the link between R1 and switch 1. Click on the link, packet capture, and then settings. I'll just add a 0 to the limit, since 50 is too few. Then I'll start the packet capture. Okay, I also want to do a packet capture on the link between R2 and switch 1, since we're sending traffic toward Server 1. So again, I'll click on that link, packet capture, and then start. Note that I already prepared a couple packet captures beforehand that we'll look at in this lab. I'll also include them with the lab files, so you can look at them if you don't have access to a lab yourself. However, if you do have CML or another platform, I recommend doing the packet captures yourself. And one more thing. I want to debug ICMP messages on R3, so we can see when it receives ICMP messages. So I'll go to the CLI of R3, enable, and then to debug ICMP messages, the command is debug IP ICMP. Okay, now let's get started generating some ICMP traffic. Note that the lab instructions for this lab are quite vague. I don't give any details about how to generate the different ICMP message types. I'll show you my solutions, but there are other ways to do this lab, so you don't have to follow what I do exactly. First, I'll generate some destination unreachable messages. R3 has a default route to R1. Let me show you that. Show IP route. There it is at the top. Next hop 192.168.123.1, R1. Now let's check R1's routing table. I'll go on the CLI of R1, enable, show IP route. So R1 has static routes to the R2-R4 link, as well as to R4's LAN, but no default route. So, if R3 tries to ping a destination that R1 doesn't have a route for, it should send ICMP destination unreachable messages back to R3. Let's return to R3 and do that. I'll ping the Google DNS server address. Ping 8.8.8.8. So, notice this U that appears here in the ping output. That means that R3 received an unreachable message. And we also get the debug messages too. Destination host unreachable received from 192.168.123.1, which is R1. So R3 sent 5 pings, but only received 3 unreachable messages from R1. That's expected. It's because there is a rate limit that determines how often R1 can send unreachable messages. The ping's output is broken up by the debug messages, but you can count 3 U's for unreachable messages And then these two periods are the echo requests that simply timed out. As I said before, I already saved some packet captures. So let's take a look at this one for the R1 switch 1 link. Messages 5, 7, 8, 10, and 12 are the ICMP echo requests that R3 sent. And then 6, 9, and 13 are the unreachables sent by R1. Let's open up message 6, specifically the encapsulated ICMP message. What's the ICMP type? It's 3, of course, Destination Unreachable. Notice the code is 1, Host Unreachable. If a Cisco IOS router doesn't have a route to the destination in its routing table, it will send a code 1 unreachable. This is different than some other vendors. For example, I tested this on my checkpoint firewall, and if it doesn't have a route to the destination, it sends a type 0, Network Unreachable. So keep in mind that the use of each code can vary, depending on the maker of the device. And inside of this ICMP message, there is an IP header and another ICMP message. Why is that? As I pointed out in the lecture video, in ICMP error messages, such as Destination Unreachable, the payload of the message is the IP header and a portion of the original message that caused the error message to be sent. Let's open up the encapsulated ICMP message. It's an echo request with identifier 0 and sequence number 0. If I look at message 5 and check the ICMP contents, notice that it also has identifier 0 and sequence number 0. So that means the Destination Unreachable message was sent as a result of this message. That's the reason the original message is encapsulated in the error message, so you know which message caused the error. Okay, so we captured some Destination Unreachable traffic. Now let's try some redirects. Because the only configured route that R3 has is a default route to R1, if I ping server 1 from R3, it will send the packets to R1, not to R2. R1 should then send a redirect message telling R3 to send the traffic to R2 instead. Let's try a ping to server 1. Ping 192.168.4.10. Okay, all of the pings worked, but notice the first message we get isn't an echo reply, but a redirect from 192.168.123.1, R1. It says, for destination 4.10, which is server 1, use gateway 123.2, which is R2. Okay, so if we ping server 1 again, R3 should send the traffic via R2, according to what we know about redirects. Let's check. Ping 192.168.4.10. Okay, this time we get a redirect again. So actually, R3 didn't listen to R1's redirect message. It sent the traffic via R1 again. The reason for this is that R3 is a router. It forwards packets according to its routing table. It doesn't listen to redirects. Maybe some routers listen to them, but these Cisco IOS routers do not. Let's check the packet capture again. Starting from message 15, we have the first ping from R3 to server 1. Message 15 is R3's first echo request, and message 16 is the redirect. Let's look at that redirect. The ICMP type of the message is 5, of course. Notice the code is 0, redirect for network. In the lecture video, I said code 0 was prohibited, and that's true. RFC 1812 explicitly says routers must not generate the redirect for network or redirect for network and type of service messages. Those are codes 0 and 2. As you'll notice during your studies, RFCs aren't always followed 100%. So in this case, R1 is telling R3, for all destinations in the same network as this host, send the packets to 192.168.123.2, which is R2. Don't send them to me. As we already saw, however, R3 ignores the redirect and continues sending the echo requests via R1. Now, this first ping from R3 to server 1 has an ID of 1, as you can see in the info column here. ID equals 1. However, there are 10 echo requests shown here with ID 1 instead of 5. Why is that? It's because we're capturing traffic in both ways. The messages reach R1, then R1 sends them back out of the same interface toward R2. So really, only 5 echo requests were sent, but each of them was captured twice. You can also know that by looking at the sequence numbers. Sequence 0, 1, 2, 3, and 4 are each shown twice. You can also look at the Ethernet header to see that. Look at message 25, sequence number 4. Notice the source and destination MAC addresses. This is from R3 to R1. Then, message 26 is the same echo request message, but the source and destination MAC addresses have changed. This time it's from R1 to R2. Then, messages 27 to 38 show the second ping from PC3 to server 1. It's the same pattern as above. R3 ignored R1's redirect, so it sends an echo request to R1 in message 27, and R1 sends another redirect in message 28. But again, R3 ignores it and continues to send the requests via R1. And like before, each message is captured twice, once when traveling to R1, and once when R1 forwards it back out of the same interface. Now I want to demonstrate how the redirect works with a Linux host, PC1. I'll return to the lab and log in to PC1. The username is Cisco and password Cisco. PC1's default gateway is R1. You can view that with the route command. Destination default, gateway 192.168.123.1. I'll ping server 1 from PC1. Note that Linux hosts, by default, will ping indefinitely. They don't stop after 5 like a Cisco router. So I'll use Ctrl-C on my keyboard to stop after 5 echo requests. Let's do that ping. Ping 192.168.4.10. And once it reaches sequence 4, I'll stop. Now, we aren't going to see any debug messages, but I'll check the packet capture after. And just in case, I'll send another 5 echo requests. Ping 192.168.4.10. And then Ctrl-C to stop once it reaches sequence number 4. So let's return to my packet capture for the R1 link. PC1's pings start at message 44. So it sends an echo request. Notice the ID of 031D. And also notice that sequence 0 is captured twice, just like before. After the first message, R1 sends a redirect, but still a couple more echo requests are sent to R1. R1 sends a second redirect, and then the echo requests stop. So it seems there was a bit of delay, but PC1 ended up listening to R1's redirect. The first few echo requests of the first ping were sent via R1, but then PC1 started sending the packet straight to R2. We can confirm that by looking at the packet capture for the R2 link. Now, we are looking at frames captured between switch 1 and R2. Starting at message 35, we again see the ping with ID 031D. 5 request messages, and 5 reply messages. Let's look at the Ethernet header. For the first 3 echo requests, the source MAC is this one ending in 08. That's R1's MAC. However, starting from the 4th request, the MAC changes to this one ending in A0. So PC1 is sending the echo requests directly to R2 instead of via R1. And then, down below, the ping with ID 031E, if I click on each of the echo requests, you can see that the MAC address is the one ending with A0, PC1's MAC. So, unlike R3, which ignored R1's redirect messages, PC1 listened to them. Now let's go back to the lab and generate some time-exceeded messages. I'll do it in 2 ways. First, from R3, I'll send a traceroute to server 1. The command is traceroute 192.168.4.10. This command is going to take some time to finish. I'll talk more about traceroute in the next video, but it works by sending packets with a TTL of 1, then a TTL of 2, then 3, then 4, etc., until reaching the final destination. This causes each router in the path to send time-exceeded messages back to the source. When packets with a TTL of 1 are sent, the first router in the path will drop the packets and send a time-exceeded message. When packets with a TTL of 2 are sent, the second router in the path will have to drop them and send time-exceeded messages. This way, the host will learn the IP address of each router in the path. Anyway, it's hard to read this traceroute output because it's being broken up by the debug messages. But notice that R3 receives time-exceeded messages from R1, then R2, then R4. And from the final destination, server 1, it actually receives a kind of Destination Unreachable message. That is, port unreachable, code 3. But as I said, I'll talk about traceroute in the next video, so that's enough for now. Next, I'll go on PC1 and do a similar thing, but instead of traceroute, I'll use ping. In Cisco IOS you can't do this, but in Linux you can specify the TTL of a ping. The command is ping 192.168.4.10-t, then the TTL. First, I'll set it to 1. I'll wait a few seconds, but no output is shown, so I'll use Ctrl-C to stop it. In Linux, if pings fail, no output is shown, unlike in Cisco IOS, where you'll see a period or some other symbol indicating the result of each echo request. So, with a TTL of 1, the ping failed. How about 2? No output again, it failed. Let's try again with a TTL of 3. Okay, this time it worked. I'll stop the ping. Now let's look at the packet capture again. Starting from message 70, you can see UDP messages. Those are the traceroute messages from R3, and then the time-exceeded messages. I'll open up message 71. Notice the ICMP type is 11 and the code is 0, meaning the TTL was exceeded in transit. Scroll down a bit in the list of packets, and from message 113, you can also see the pings from PC1 and the time-exceeded messages it received. Okay, so we've seen all of the message types from the lecture video. Before wrapping up, I want to demonstrate one more kind of Destination Unreachable, the fragmentation needed message. Back in the lab, I'll go on R2 and configure its G01 interface. That's the interface connected to R4. Enable conf-t interface G01. I'll set the IPMTU below the default with the command IPMTU 1400. Okay, now let's send a ping greater than 1400 bytes with the DF bit set, so R2 has to drop the requests. I'll go on R3 to do that. Let's ping server 1. Ping 192.168.4.10. I'll make its size 1450, and then DF bit. Okay, for the host unreachable messages R3 received from R1 before, it showed a U in the ping output. But notice this time it is M. That means it received a fragmentation needed message. And you can see that in the debug output too. There are redirect messages from R1 again, because R3 can't listen to orders, but also 3 fragmentation needed messages from R2. Notice it says MTU 1400. So R2 tells R3 its MTU value, the value of 1400 I just configured on it. Again, even though R3 sent 5 echo requests, it only received 3 unreachable messages. That's because there is a rate limit, controlling how often R2 sends unreachables. Anyway, let's take a quick look at the packet capture. Down at the bottom, we can see the echo requests from R3 and the fragmentation needed messages. I'll open up message 146. The ICMP type of this message is 3, because it's a Destination Unreachable message. And the code is 4, meaning fragmentation needed. Okay, in this lab, we generated some ICMP traffic in the network and looked at debug messages and packet captures to analyze it. In this video, I went pretty quickly through the lab, but I highly recommend doing the lab yourself and spending some time analyzing the ICMP traffic to really understand it. There's a big difference between watching me go through the lab while explaining a few points and actually doing it yourself and analyzing the results. That's all for this video. Thanks for watching. Before finishing this video, let me thank my JCNP level channel members. To become a member, please click the Join button under the video. Thanks to Jonathan Makara, Velvajakum, George Streeter, Funny Dart, Nasir Chowdhury, Devin Suku, Gustavo B.R., Gerard Baker, Marcel Lord, Pavel M., Mr. Erlison, Dragos Hirnea, Zakib Shah, Mayor Salman, Mason Anderson, Vithouse194, Gina Lindley, Mark Jackson, Bold1C1U, Michael Carroll, Gerald Guillaume, Gabriel Braga, Renan Marias, Hector Hernandez, Maratuba, Roji Kuriakos, Arpad Konives, 5 Feet, Owad, Daniel Brown, Tricky Mickey 123456, Scott Thompson, Jose Alvarez, Kevin Hayes, Hussein Yavuz, Samuel Tavares, Mustafa Ersoy, Dear Diso, Nasser Zahar, Alexandru Badic, Brian Grant, Georgi Gemejev, Dibya Swain, Arlen Plagaria, Adelson Pereira, Farad69, Lucian Stoichitoyu, Madmark 50484, Sean Powell, Alexandru Stratan, Hiago Bicalho, Pradeep Halder, Piotr Kaimov, Abubakar Berry, and DMJ2. Sorry if I pronounced your name incorrectly, but thank you so much for your support. Thanks to you and my other supporters, I am able to make these videos and release them for free on YouTube, so I really appreciate the support. Another great way to support the channel is to like the video, leave a comment, subscribe, and most importantly, share this video with others. So, if this video was helpful, I'd appreciate it if you did any of those. Thanks for watching.